Hey guys, how's it going? So in this tutorial, I'll be showing you guys how to perform a number of matrix operations such as defining a matrix, multiplying it to matrices, or adding or subtracting to matrices, and even how to calculate their eigenvalues, determinant, inverse, transpose, etc. using Python. So in one of my previous tutorial, I already showed you guys how to install Python as well as the necessary libraries for scientific programming. So in this tutorial, we'll be using two of those libraries. So the first one would be NumPy. So what we are going to do is we are going to import it by typing import NumPy as np. So what this will do is it will let us access the functions available in NumPy by referring them using np. And the next library we are going to need is the SciPy library. So we'll import that, and rather what we'll do is we'll only import the necessary part from that library. So we'll write from SciPy import linalg. So linalg is the linear algebra module from SciPy, so we'll be importing that. And what we can also do is we can import it as lg so that we don't have to type a lot. So now we have imported SciPy and NumPy. So the first thing we'll be doing is we'll be defining a matrix. So let's call this matrix A, and we'll define it by using NumPy arrays. So the way to define NumPy arrays is to write np.array. Now make sure that you have also imported NumPy as np if you're going to write np.array, or you can even just write import NumPy and then you can write numpy.array. So you get it right. So and then you will have parentheses. Now the important thing is, in order to define a matrix, you cannot just use a single dimensional array, a single dimensional NumPy array to be exact. So you'll need to use two-dimensional arrays. Therefore what you'll do is you'll write parentheses and then you'll write square brackets, and then within those square brackets you will enter the elements of the matrix row wise. So what that means, let's say the matrix is a 2 by 2 matrix with the first row 1 2 and the second row is 3 4. So what we'll do is we'll write 1 comma 2 within square brackets, and then we will write 3 comma 4 within square brackets as well. So here are the elements of the matrix. So you have np.array parentheses and square brackets, and then within those square brackets you have the elements of the rows within square brackets and separated by commas. So that is the first matrix, that is A. And then we can define matrix B as well. Similarly, np.array and then parentheses, square brackets, and then within those square brackets we can have the value of the elements. So we have 5 comma 1. So now we have defined two matrices, right? So we have a matrix B and we have a matrix A. So the next thing we'll do is we will perform simple operations such as adding the matrices. So we'll write sum equals A plus B, and then we can subtract them also. So we'll write difference equals A minus B simply. So that is pretty easy. And then we can multiply them as well. So we'll write product equals and also I'm noticing that sum is kind of weird out, so we'll write it sum 1, and then we have product equals, so probably sum is defined within NumPy or something, I'm not really sure. So we'll have prod equals so this is interesting. In order to multiply the matrices, what you're going to do is you are going to use the command dot. So here's how it goes. So a dot, and then within parentheses you will write the matrix with which you want to multiply the matrix with. So that is how you perform a multiplication of matrices using the dot command. So you have a, and then you have a full stop or a period, and then you write dot, and then within parentheses you write B. So that will multiply A with B. And also make sure that the matrix A has the same number of columns as the number of rows in matrix B for the product to be defined. And then what we can do is we can also calculate the transpose of A, and let's call it transpose, and that would be equal to A dot T. So that is how you will define, So that is how you will define the transpose. So that are some pretty simple operations, and then you can also calculate the determinant of a square matrix. So in our case, we have already defined the matrices as square matrices, so we can write determinant equals det. Yeah, and also now one more thing. So this time we cannot just use det like this, because we have to use LG. So det is in fact a function within the SciPy library. So we'll use lg.det, and then we'll write down the name of the matrix. So determinant of B, let's say we are evaluating, and then we can also calculate the let me see. So yeah, we can also calculate the inverse. So we can do inverse equals LG, which is how we are referring to the linear algebra library in SciPy, and then lg.inv and then B. So that will help us evaluate the inverse of matrix B. And then finally, in order to get the eigenvalues and the eigenvectors of matrices, of square matrices to be precise, you will do what you'll do is you will write down a matrix A and a matrix B, and let me just rather call them values and vectors. That is more intuitive. So we'll define two matrices which are equal to Eig, which is also within LG, so lg.I, and then within parentheses you will write the name of the matrix whose eigenvalues you are evaluating. So what this will do is this Eig function will return two sets of arrays. The first would be a single dimensional array which would contain the eigenvalues, and the second array, which is called vectors, would be a two-dimensional array, and its columns would be the eigenvectors corresponding to the eigenvalues within the first array. So the ith eigenvalue corresponds to the ith column of the vectors matrix, right? So if that makes sense, I hope it does. So that is all. That is how you can perform a number of matrix operations. So now what we are going to do is we are going to run this program that we have written here. I've named it, or rather saved it, as matrix operations.py. So let's go ahead and run it by giving the command python3 matrix operations.py and see what happens. Yeah, nothing, because so it's a good thing that nothing happened, because that meant that we didn't face any errors. But since it didn't print anything, because my stupid ass forgot to give the print statement, so we'll write print A to print the first matrix, then we'll write print B to print the second matrix first of all, to see if our matrix initializations were properly done. So as you can see, the first matrix is 1 2 3 4, so each element or each square bracket is rather row wise, and then the second matrix, which is 6 1 5 1, is also printed out. Then we can print out the remaining things, such as print sum, and then we can similarly print out like a difference. Then we can print out the, let me see, product. Then we will print out the transpose, and then we will print out the determinant, and then we can print out the inverse. Sorry. Yeah, and then finally we'll print out the eigenvalues and then the eigenvectors. So that is it. Now let's go ahead and run this program again after saving this code, and then now you can see that here we have the matrix A, we have the matrix B, and then we have a problem such as like built-in function sum. Yeah, that is what I was suspecting there when I was typing sum. So that is why I pretty much changed it. Oh yeah, so in print statement I forgot to give sum1, I rather gave sum. Okay, so now it is correct, and let's just go ahead and clear this and print it once again. Okay, so we have the A matrix, B matrix, and then we have the sum matrix. So as you can see, 1 plus 6 7, 2 plus 1 3, 3 plus 5 8, and 4 plus 1 5. So the sum is also correct. And then we have the difference, so which is here. So 1 minus 6 is minus 5, 2 minus 1 is 1, and then 3 minus 5 is minus 2, 4 minus 1 is 3, so the difference is correct as well. And then we have the product. So the product matrix is this one, so it also seems correct to me. And then we have the transpose, so transpose of the let me see which matrix, A. So the transpose of A matrix is 1 3 2 4. So are we getting that? Yeah, we are getting 1 3 2 4. And then we have the determinant of B matrix, and that is 1. As you can clearly see over here, 6 minus 5 equals 1. So due to some numerical precision errors, are especially because of the floating point representations, it's not exactly 1, but it's approximately 1. So, and then what we have is we have the inverse, which is 1 minus 5 6, and I'm pretty sure it is correct. And then we have values, which is the eigenvalues of the matrix B. So these are the eigenvalues of the matrix B, that is 6.854 and 0.14589. And also you can see that these eigenvalues are in complex notation. However, the imaginary part is 0, but it can also be the case that the eigenvalues are complex, therefore they are printed out in the complex notation. And then the eigenvectors corresponding to each of the eigenvalues is this. So the first column, that is 0.76 and 0.649, corresponds to the first eigenvalue, and the second column corresponds to the second eigenvalue. So that is pretty much it. That is how you perform a lot of matrix operations using Python and the SciPy and NumPy libraries, and also a lot of operations defined within the SciPy library and the linear algebra module are also accessible within the NumPy library. But I read somewhere that the SciPy module or the functions are more optimized and take the advantage of a lot of Fortran and C++ code. Therefore they should be faster than using the NumPy functions for the same application. So I hope you guys enjoyed this tutorial. In case you did, then don't forget to hit the like button and subscribe to my channel for more videos like this. Thanks for watching and have a great day.